So let's work out which conductor's which. We've got to presume that one end is saying a fire alarm panel and one end is saying a break glass. We've got them both in front of us, but we've got to think about that. So let's go to the end with the panel and we pick a conductor. Doesn't matter which one we pick. So we pick a conductor and we link it to the actual body itself. That's saying the panel for the fire alarm. We walk out, we go to the break glass, instrument set up for ohms, and we're going to clip one of them onto the actual outside circuit protective conductor and one of them onto a conductor. We don't know which one's which, so hopefully when we know we've found the right conductor, we'll get a low reading ohm. Let's have a look. We have, first time out, 0.03, but let's just prove that. If I'd have connected onto this conductor, you can clearly see I have no reading whatsoever. So let's go back to that one. So I've identified that conductor to be the one that's linked this end. So those two conductors, one in the panel, one obviously at the break glass, are a conductor. We can make it the neutral, we can make it the line, it doesn't matter. So how are we going to do that? Simply by over sleeving it. So in this case, I'm going to take some blue sleeving. I'm going to slide it on here and identify it as my neutral. And likewise at the other end, we can identify that one as a neutral. I'll prove the same point again though, so let's prove it anyhow. I wouldn't do this on site, I'd be happy with my decision at that stage, but let's prove that this was the line. So if we link these two together, the crocodile clip will hold on. Come on, there we go. So we link these two together. If we come down here, we go onto the body and we go onto here. We expect to see a low reading ohm meter identified that conductor. You only need to identify one of the conductors, unless you're working with a 7 core, then obviously the process continues on, etc. So this time we're going to identify it with some brown sleeving, like so, on both ends. So brown sleeving goes on there. This one's a little bit tight. I was a bit worried that will go on. That goes on perfectly. Got a slightly fatter one here, just to make life a little bit easier for me. So again, we identify those conductors at both ends. So there we have it. We've identified the conductors so we can use them in circuit. It might be if it's for a fire alarm system that you may want to identify it slightly different. I'm presuming we're using this in our workshop for a 230 volt circuit. So we're turned into the electrical workshop, and what we're going to do is give this a good whack. We know it's fire resistive. We know it needs to be held in using metallic fixings from discussions in the classroom, because when it gets red hot, we don't want it to move. In other words, it could shatter. So that's why we're using metallic fixings on fire resistive cables. It happens to coincide with the rules for premature collapsing, but that's by default. But I want to show how mechanically strong or robust it is by actually giving it a bit of a whack with a hammer. So if we do an insulation resistance test on it like so, so if I put those on like there, and then I do an insulation resistance test, if you can see the instrument, you can see it's greater than the machine can read, and I can do it to earth as well. We've had that before. So what I'm going to do now is I'm going to give it a few little whacks. You might find that I drop the sound off at this stage because obviously the mic's going to be here, but I'm going to give this a few little whacks. I now see it isn't round, so we'll give it a little bit of a whack. Let's try the old insulation resistance test again. Oh, greater than 999. Well, let's just confirm that by going between live conductors to earth. Let's just do that, to live conductors to earth. Let's get them together. I don't want any jiggery pokery. Ah, okay. We go again. It's a bit harder this time, I guess. If you look at that cable there, that's looking not round anymore. Do we agree, audience? Can we see that? Does that look round? Okay, so we'll give it a bit of a whack. Let's try the insulation resistance test again. We have got greater than the machine can read. Let's go between the conductors to prove we're not doing anything again. Little jiggery pokery. There we go, greater than the machine can read. I whack it again. That's got it. That was a spider. You wouldn't think it would still be with us. Let's have a look. Dead short. Okay, we're at the stage now we've got dead short. Let's prove and see if we've got a short to earth as well. Actually, we haven't. Okay, that one's clear. And let's try this one here. Actually, it's only shorted out between the conductors. Obviously, at that stage, it has failed. If you just look at that, okay, can you see that okay? Yeah, so you can look at that, how flat we had to get it in order for that cable to actually fail. And that's hitting it onto a metal surface with a blunt object in the form of a hammer. It's dead flat almost there. So we were at stage 3 or 4 of hitting it before we actually caused that to obviously break down as a cable itself. So not only is the cable fire resistive, we know the ends aren't. These tend to be attached to plastic emergency light fittings, plastic backed bells for alarm systems and brake glasses. So we know the cable itself is fire resistive and the actual pots that we put on aren't, but we also now know it's a highly robust cable, okay, if you hit it with a blunt object. So let's hit it with a non-blunt object in a different area. So an area that hasn't been hit, let's hit it with a non-blunt object. So if I was to hit it with a screwdriver and a hammer, you can see straight away and through there. So it's sharp objects. It won't be as strong mechanically, but certainly you can give it a good whack with a blunt object.